Hello everyone, I'm Cosimo. I'm a PhD student at the University of Bergen. And today I will give a presentation about a joint work, mainly in collaboration with Arnold Zaki, my supervisor. And it is about extracting rules from trained black box machine learning models like neural networks from data made of partial interpretation. I will explain everything soon. This work is mainly motivated by the need of finding explanation of predictions made by black box machine learning models, because these models are now used for high stakes decisions. For example, we know that there are people now that have been denied parole and also during criminal justice, there are people that are being accused of being sex offenders because of some positive tests for having a positive test for a DNA test. Then we have air pollution. So we have models that predicted high pollution levels, even though so low pollution levels, even though actually in reality the air was highly polluted, and this affected the health of people living in the neighborhood of these areas. And also we have these models that denied the approval of loan to some people, even though because of high bias in the training model of during the training of these models. So in particular, in this last case, we have this example that it was the only one in which we clearly know what went wrong. Is that there was a person in this model, the feature, an important feature was a surname, because it highly correlated with the ethnicity and religion. It was a high predictor that both those two were high predictors of how a good person was able to give money back. And so in the test phase, this was really a really nice feature to have, but it created a high bias. But if we have a way of actually seeing what are the features and how the predictions are made, then we're able to solve the problems when we have them, when we find the errors in these models, or even better, to check for errors before putting them into production. So with our method, we assume that we have a trained neural network model, and then we want to have interpretable rules that have as an antecedent the set of features that describe an example, such that that example is assigned a specific class. To extract rules, we use an algorithm that is already present in literature, and it works under the learning from entailment settings. That is where the algorithm assumes that it can receive examples from formulas directly described as formulas. But in this case, we adapted the learning algorithm in such a way that the examples that can be received are partial interpretations. This is why we extract rules. In the title, we have partial interpretations. Before continuing in the explanation of the method which we are able to extract rules, I would like to show what are the rules that we can extract. And those rules are expressible in the form of Horn logic that can be considered as a set. So with logic, we express implications. This means that in this implication, we have an antecedent and a consequent, where we have an antecedent as a conjunction of formulas that if set all to true, then this formula constraint variable to be set to true. Like for example, if we have that both variables v1 and v2 are set to true, then this constraint is saying also v3 must be set to true. Another constraint we may express is the constraint in which if variable v4 and v5 are set to true, then we have a contradiction. So this means that we don't want in our formalization that both those two variables are set to true. We give meaning we assign meaning to these formulas by means of interpretation. It can be considered as an assignment, as a worldview that says what's true and what's false. In addition, since we consider partial interpretations, we also have the possibility of expressing if a variable is unknown. So we don't know if a variable is set to true or false. And it's especially useful when we would like to, during training phase, because it's not always the case that we have all the features of a specific example specified. We also use another representation of interpretations, which we have a list in which the ith argument of that list corresponds to the truth value of the ith variable. So for example, the first argument here is set to 0, and this means that the variable 1 is set to false. The second argument, this means that it's set to 1, this means that the variable 2 is set to true. And here, for example, we have variable 4 that is unknown. And this, yes, so then we have that interpretation falsifies a rule if and only if we have that every variable is in antecedent set to 1, so it's set to true, and consequence is set to 0. We can consider an interpretation as a set, an assignment of those features, as said before. And given a set, we consider each classified interpretation as a classified example. So in our implementation, in the end, when we have a set of classified example, we actually have a data set. And this dataset describes if it contains examples, and each example describes if the rules in an abstract target are satisfied or not. Like for example, in this first row, we have that variable 4 and 5 are set to true, and this falsifies this constraint. So the final classification of this partial interpretation would be 0. Or if we consider this second row, we have that all constraints are satisfied. So the final classification of the partial interpretation is 1. So assuming that we have this set of classified partial interpretations, we would like to find, by just looking at the labels and partial interpretation, the rules that hold according to this dataset. We can train a neural network model according to this information, but then what we are missing is actually the rules. So we actually don't know what are the rules. We just know what are the if a given partial interpretation satisfies or falsifies. In order to obtain these rules, then we extract with the Horn learning algorithm. And the Horn learning algorithm is assumes neural network to answer truthfully to its questions. So the algorithm will act as a student, and the neural network as a teacher. Assuming that the trained neural network encodes a Horn theory, we run the Horn learning algorithm, and we let the neural network answer its questions. There are two types of questions that this algorithm can ask. One is called a membership query, where the learner sends a partial interpretation, and the neural network checks if the partial interpretation satisfies the target. This corresponds in saying that the Horn algorithm will send an interpretation, we call the neural network with that interpretation as input, and then we obtain the classification. Is that the classification corresponds to no, this partial interpretation does not satisfy the target, then the Horn algorithm will generate clauses, formulas, constraints that satisfy this condition. Otherwise, if given as input another partial interpretation and the neural network classifies this partial interpretation as yes, then this means that the partial interpretation satisfies the neural network, the target, then the learner will revise its built formulas. The second query is called equivalence query. The algorithm will send its entire hypothesis, and it will check if the target is equivalent to the hypothesis. And when a counterexample is found, then the learning algorithm will receive such counterexample. It is something that either is satisfied by the target but not by the hypothesis, vice versa. And the algorithm will use that counterexample to revise the current hypothesis. Eventually, the algorithm will found an equivalent hypothesis, and at this point, the algorithm will stop. So with our strategy, we assume that we can train a neural network with partial interpretations, and these partial interpretations classified. And then we obtain a neural network that encodes a Horn theory. So it's a set of Horn rules. And then we start the Horn algorithm that will ask queries to the neural network, and in such a way that the algorithm will find a hypothesis that is equivalent to the rules that are encoded in the neural network. Simulating a membership query is easy because this corresponds to so when the algorithm sends an interpretation, this interpretation is sent to the neural network, and the classification corresponds to the answer of the membership query. When simulating an equivalence query is more difficult because we would need to check the entire truth table with that method. In order to make this approach feasible, we use a result in the literature in which that states if we select a big sample that of interpretation created randomly and classified by a neural network, then if this is big enough, we can search for a counterexample, and the hypothesis built in this way, when we return a counterexample found in this big sample, then we can guarantee some probabilistic properties of the generated hypothesis. Okay, in the last part of this presentation, I would like to explain our results. So we selected the human carcinoma dataset that contains also unknown values of unknown values of some features, and this dataset describes patients that have been diagnosed cancer, and they've been described by some features like if they are smokers, if they're young, if they have saturation in oxygen, if they have high iron levels in their blood. And the classification is if that patient will survive after 1 year or will not survive. So we can assume that we have a data set of this type, which we have variables in this data set. We have around 200 features, binarized features, and we can translate this partial interpretation into, so assuming that we have this dataset, we can transform the dataset into a target theory that describes the rules that should be met in order to satisfy these conditions present in the dataset. For example, if we have that there's no aero saturation and that person is a smoker and comes from an endemic country, then this means that he will not survive after 1 year. Or if it has oxygen saturated and iron, a lot of iron in the blood, and it is young, then it will survive. So we generate our own theory in this way, and then we generate randomly partial interpretations that will either satisfy or falsify the abstract target. We then train a neural network according to the data we generate in this way, and then we run the Horn algorithm. We limited the Horn algorithm to just 100 equivalence queries that it can ask, and afterwards it stopped. And then we compared the performance of the rules generated by the Horn algorithm with the target theory, the neural network, and a decision tree. So we compared our methodology with the extracting a decision tree that is also an interpretable model. And the results are good, I would say. So we have that at most 9 to 9.2% of those interpretations generated randomly, the classification between the hypotheses extracted by the neural network and the target differ. But I have to specify this is when we limited the number of equivalence queries to 100. If we increase the number of equivalence queries, then the quality of the hypothesis will definitely increase too. Then in this column, we have the difference of differently classified interpretation between the target and neural network, the target and the tree. Yes, so I've concluded my presentation by describing again our methodology. We assume that we have a trained neural network model, and our goal is to extract Horn rules. We use the Horn algorithm that works in the exact learning model that asks queries to the neural network, treating it as a teacher. And when the teacher is assumed that it answers truthfully questions, then the algorithm will is guaranteed to output a set of rules that are that hold according to the target, in this case, that is encoded by the neural network. Okay, I conclude my presentation. I will thank you for your attention.